I will try to convince you that studying supernova is really interesting if you are not already convinced. And my goal is to know what type of star explodes as a supernova. And I think, and I will try to convince you that if I know this, I will know many things and all the questions of the universe will be answered, more or less. I particularly study hydrogen-rich supernovae. Maybe you are more familiarized with type 1As that are very known for being useful for cosmology. We are trying to use other types of supernova for cosmology as well. And the goal of my talk is to discuss the implications of the observational study for theoretical models. I am not a theoretician, so my intention is just to trigger discussion, questions, and maybe me asking you rather than you asking. I will end up by discussing the possibilities and challenges. Supernova is the explosive death of stars. This would be either a massive star that generates an iron core in its interior during evolution and ends up exploding because of the core collapse, or it could be a white dwarf in a binary system, which for some reason acquire enough mass to surpass the limit of mass of Chandrasekhar, which is the limit of mass at which a white dwarf is stable. And then after this limit is reached, there is degeneracy in the nucleus of the star that leads to a thermonuclear runaway and a subsequent explosion. Why do I study supernova? Now we are all clear about what a supernova is, I hope. We study supernova because when a star explodes, it expels all the elements that were formed in its interior. The stars are the only natural nuclear reactor that we know, and so by studying the ejecta of a supernova, we can know a lot about these elements. We also study them because when a supernova expels all this material into their host galaxy, into the galaxy that is hosting them, it enriches the medium in where they are, and this could also trigger star-forming events. So it also tells us about the evolution of the galaxy. It also, supernova can help us understand what's the shape of the universe we live in. Supernova have been used to discover the universe was accelerated, and if we get to observe more distant events, we get to know our universe further and further. When a massive star explodes, they leave behind a compact remnant. This is a neutron star or a black hole. And so studying the supernova will also tell us a bit about the nature of the remnant that they are leaving behind. These are usually in the lower mass ends, and nowadays they are quite popular because of LIGO, Virgo, Cagra. We know a lot about gravitational waves, but we don't really know that much about how these binary systems are formed before they merge to create the gravitational waves. So we think that supernova can lead us to know better. And since we are talking about gravitational waves, when a supernova explodes, then gravitational waves are also generated just because of the explosion. Sadly, current detectors are not able to reach the frequency of these gravitational waves, but we are moving towards that. And also because supernova is cool and many people name their movies after it, so it's very nice to study supernova, if not only for that. So why do I study samples? Well, I think we are in a survey era, what I call the LSST era. Since a couple of years now, decade maybe, large surveys have discovered more and more transients. Before, we were discovering a couple of tens of supernova per month with large surveys that scan the sky every night. We went to thousands of transients per month. And with LSST, which is the upcoming big survey with a big field of view that will go very deep and that will scan the whole sky every couple of days, we will have millions of events. And we need to be prepared to handle all this data. What we need to do is to know what are the most useful events, what are the events that will tell us the most about the physics of the stellar explosion. And for this, we need to know what are the common objects as well. And so with samples, we could distinguish, okay, this is a common event that behaves as these all others. And then I have this one that I can cherry pick because it has so many different characteristics. How do we classify supernova? So supernova occur in galaxies, and they can become as bright as the host galaxy at some point, as you can see here in this movie. Here is the supernova going off in this galaxy. When it's bright, it reaches a peak in the light curve, and it emits a very characteristic spectrum. Based on the spectrum, empirically, we can classify the type of supernova. So if there is hydrogen, then we will say it's a type 2, and if it's not hydrogen, we will say it's a type 1. I will not care about all the type 1s, but I will care about the hydrogen rich. And in particular, there is a transitional class of events that is classified as type 2b, because they show a lot of hydrogen, but at the beginning, but soon after peak, this hydrogen disappears, and it only shows helium. Luckily, this spectral characteristic kind of correlate with the shape of the light curve that we see. We could say, okay, this light curve is shaped as a type 2, and then we can classify it without the need of a spectrum. And this is the whole point of studying samples, to need every time less observational data to be able to say, okay, this is this object. And we classify empirically, but this can very much be associated to physical progenitors and to physical characteristics of the exploding star. In particular, if we see hydrogen in the spectrum of a supernova, we have to assume that this hydrogen was in the star that exploded. If we consider the star as an onion with different layers of material, the outermost layer will be hydrogen, and if we see this hydrogen throughout the whole spectral series of the supernova, we say, okay, this hydrogen was there when the supernova exploded. In the case of type 2b's, for example, we see this hydrogen early on, but then it disappears. So we consider that the star lost somehow part of this hydrogen envelope, but not all of it. Some remain, but we don't see it throughout the whole entire spectral evolution. So it was not the whole thing there. There are also several studies that study the correlation between the observational parameters that you can see here. These are different observational parameters to physical parameters that you can obtain through models. And then you can associate observed parameters to theoretical models of supernova. And this is the work of Martinez et al. 2022. Galliam in 2017 did a recollection of all we know up to now and associated different types very directly to different type of supernova very directly to different type of stars. In particular, the ones I'm interested in are associated to massive stars, and this has been found with theoretical models, but also confirmed by serendipitous detection of progenitor stars. This is a supernova goes off, then we go back in time and check all the observations that were done historically of this the site of the supernova, and maybe if the galaxy is close enough, we can resolve a star there and say, okay, this star was associated to this event. So, hydrogen-rich supernova. The first study I did was between comparing type 2 and type 2b. Why? Because in 2012, Arkavi et al. Did a study of, at the time, a very large sample of events, and found that there are 3 types of light curves that stay, all of them, in their own boxes, defining 3 different classes of events. Among the type 2, these 2 classes of events were already known and were called type 2p, because the light curve shows the plateau before decline, and type 2l because they decline linearly after peak. And then you had the type 2b that were more, let's say, bell-shaped. And there are study of these shapes of these light curves, concluded that there were 3 different classes. So we should assume that they were coming from different progenitors, or the progenitors were experiencing different things before exploding. However, Anderson et al. In 2014 did a study of much larger sample of only type 2 supernovae, and those were called type 2p and type 2l, and discovered that there is in fact a continuum between these light curves, which can lead you to believe there is a continuum in the explosion mechanism for these events. So they are not anymore type 2p and type 2l alone in their own boxes, but it's a continuum class of events that corresponds to a continuum in physical properties of the explosions. So we took over from this work and decided to add the type 2b's. Our problem here is that we didn't have a really nice, well-curated sample of type 2s as Anderson et al. And they had their sample was obtained through the Carnegie Supernova project with the same instruments, reduced in the same way, very, very nice sample. But there was not such a thing for type 2b, so we had to go into the published event, and we recollect information from different sources, and we need to treat homogeneously all this data coming from all different places. So what we decided to do, since we were only interested on the shape, in the shape of the light curves, was to interpolate them with Gaussian process. Here you can see the interpolation in blue, and in light blue you can see the region of confidence of this interpolation for this light curve that has so different data coming from different places. The shape is there, and this is what we are interested in. So we interpolate all the type 2b's and the type 2s, and here you can see the light curves of the type 2s in red and cyan the type 2b's, and you can already say, okay, there doesn't seem to be a continuum there. But we studied several parameters, and we found out they are actually very different type of events. The most striking parameter is the rise time, which is the elapsed time between the explosion at the maximum here of the light curve. So this rise time is much longer for type 2b's, already separating this class. We went a bit further and decided to derive the interpolations with respect to time. And the first derivative gives information about the slopes, and the second derivative gives information about the curvature of the light curves. And so we compare these parameters to the rise time, and we again find 2 different groups. We did several statistical tests, again finding always only 2 groups. And so we say, okay, these are different events. They come from different type of progenitors. How do we go to luminous events? Well, in the work of Anderson et al. In 2014, there is a lack of events that are brighter than minus 18.5 magnitudes. And in the literature, there is only a handful of events that are this bright. So we decided to make a sample. We use PESTO. We recollect the sample through the PESTO collaboration, which observed with the entity telescope at La Silla. And here, maybe you can see, maybe. In solid lines, it's our sample. So you have these, in this case, it's only 6 events. And what we can see is that there is not a given shape. We compare our sample with the ones that were publicly available, and there is no striking shape or continuum of shape that you can say, okay, this is a continuum of events here.
Sorry.
Yes.
It seems that it is not that before the maximum light, so very few cases.
There is very few cases, yes. And this was the one interesting find, is that all these events are fast decliners. So yes, so our luminous events are very fast declining. So what we think is that they were so fast that we were not able to catch the maximum of the light curve because it was fast and we just missed it. And this happens many times.
Fast rising, fast.
Yes, this is our assumption because we think that otherwise we would have picked the we would have observed the peak. And you can see in other cases when you observe the peak, they rise very fast anyway. We also see that they are very blue when we compare to normal type. We compare to the sample of the Jaeger et al. In 2018, and these are normal type 2 supernova. The ones they were same ones as the work of Anderson et al. 2014, and these are our events compared to some other supernova available in the literature. And so we find, okay, then we have yet another class of events that is coming from some different type of progenitor, but there are still type 2s, they still show hydrogen. So what's going on? we go further and we go to superluminous supernova. Superluminous supernova, in this case type 2. Again, the classification is empirical from spectral features. So again, we see hydrogen in the spectra. And in this case, luminous or superluminous is just arbitrary classification based on the brightness of the peak of the light. And in this case, I present a sample of superluminous supernova obtained with CEF, which is another big survey that scans the northern sky. In G, R, and I, here they are only overplotted, all the light curves normalized to the time of maximum and just overplotted. In density scale, you can see brighter points where there are more density of points, and you can see darker points where there is less observation. And we study some time parameters that we call T rise and decay 10 and T rise and decay 1 over E. And we say, okay, the rise times are more or less homogeneous. They take so long to rise though. When before we had like 20 days or less to reach to the maximum light of to the peak of the light curve. In this case, in the case of superluminous events, we take hundreds of days. Well, most. It's like between 60 to 100 days to reach to the peak.
Sorry, the rise time for the superluminous supernova is 60 days?
Yes. Yes.
But for the luminous?
There is 20 or less, which is usually much less than 20. It tends to be in the order of 10. And if we look at the decline rate, we see, okay, in this density plots, there seems to be a bimodality. So maybe there is even like among the same type of events, there's more diversity in the progenitors. But when we study the distribution of the decay slopes, we don't see bimodality. Although this is very much work in progress. This is the the project I'm working on right now. So we need more results. But already quite interesting. What is more interesting is that if we avoid observing the sample as a whole and we observe each event on their own, we see that there are some weirdos that, okay, this didn't rise that fast. This didn't rise that fast. This has 2 peaks instead of 1. This has a weird plateau before declining again. So there is variety inside the variety of events that we are observing. And here is the point where I want to discuss the most. What are the implications of this finding for theoretical? Well, in the case of type 2 versus type 2b, this is the supernovae that show hydrogen the whole evolution versus the ones that don't show this hydrogen throughout the whole evolution, meaning that they must have lost it during the evolution of the progenitor. We find that if we do hydrodynamical modeling of a normal star with hydrogen in the envelope, and we start removing the mass of hydrogen of the star before it explodes, we never reach the shape, the bell shape characteristic of type 2. We see the plateau, we see shorter plateau, we see the linear decay, but never the bell shape. And this mass was lost just through winds. So this is not a good mechanism to explain this diversity, at least not with these models that we are using. Here, I show you what is the shape that we were looking for that we didn't find. And this shape is consistent. You can see this in the work by Bersen et al. In 2012. This shape, this bell shape, is consistent even if you modify the energy of the explosion of the star, but also if you modify the mass of the progenitor. So again, single evolution models cannot explain this diversity. In 2018, Eldridge et al. Consider binarity. So they say, okay, if we consider progenitors in a binary system, and then in this case, mass loss can occur through mass ejecta to mass transfer to a companion. And then we explode these stars, and then we recover all the shapes, the plateau, the linear declines, and the bell shape. And they showed these in different bands, and they claim that it's binarity that explains the diversity. However, when you compare the models to the observed data, you can see that the bell shape is not so accurate compared to, so it cannot translate that well to the observations. In this case, these light curves that are here classified as type 2b, they rise too fast and they decline too fast, and they don't have this curvature after peak that we observe. So although binarity can be a mechanism explaining this, and binary stars have been associated to type 2b events, it's more difficult to see right away from a set of models that this is strikingly the case. For luminous events, we compare to models that have circumstellar material. So massive stars lose, we know this from stellar evolution, massive stars lose mass from the envelopes through their evolution. Even though we still see hydrogen in the evolution of the supernova, we know massive stars have winds. And this wind, we believe, creates circumstellar material. And so when the supernova explodes, the ejecta interacts with this material and can boost the luminosity of the light. And we compare these two models, and in this case, we cheat a bit because we are also comparing the spectra, and we say, okay, the light curve at late times is maybe not that similar, but the spectra is quite similar. And in this case, again, these models were not tuned to fit the observations. And in the case of binary events, these models are presented as is. They take a prototypical star and they explode it. And we believe that if either before or in this case, we tune the models to observations, we will get better matches. But still, we are looking for the one mechanism that makes this happen, right? The one mechanism that we can say, okay, this is what is going on with the supernova explosions. So it is binarity, it is TSM, it's a combination. So what's happening with the superluminous supernova? Well, in this case, Orellana et al. In 2018 compare observations to a magnetar model. And this is the luminosity of the supernova is boosted by a spin down of a magnetar. This is a very highly magnetized neutron star that is generated as a compact remnant, and can explain very well the high luminosities, but also the large rise time. And in this case, you say, okay, so we have binaries, we have CSM, and we have things that are creating compact remnants, but not all of the supernova create the same compact remnants. But moreover, same characteristics can be explained by different models. And in this case, Terreran et al. In 2017 compare the observations to pair instability models. And now when I say pair instability supernova, we are talking about completely different kind of progenitor. Pair instability supernova occur for very, very, very massive stars. In this case, are we okay?
No, no, yeah, sorry.
Okay. In this case, if we again consider these layers in an onion, when the core of this onion is made of oxygen, because it's so massive, it starts creating pairs. And at some point, creates so many pairs that the nucleus becomes unstable and creates a thermonuclear runaway and generates an explosion as supernova. In this case, there is no remnant behind. So we can explain superluminous supernova, but by either complex compact remnant or no remnant at all. And when we go to the observations, we see that the most likely pair instability supernova to date is not a type 2. So Schulz et al. Present their work on this event, supernova 2019 IBB. And this is a supernova that shows no hydrogen. So the progenitor star was stripped of all this hydrogen, and this should be a massive amount of hydrogen if this was a supermassive star as we are mentioning here. And also, how do we generate these so massive stars? Among core collapse supernova, there is the so-called red supergiant problem, which basically is we are finding that the progenitors of the supernova that we observe are in the lower end of the mass distribution of a massive star. So in this case, we're saying, okay, but this was way more massive, and we found so few events. And the events we find are without hydrogen somehow. We think that if we could observe very, very far away to earlier stars, we could observe instability supernova arising from population 3 stars. And this could help us understand better. If you say, okay, this is happening because your star went through a different evolutionary channel. It's a different type of star. It's earlier, had a different chemical distribution. However, again, there are more problems. Things that we need to consider is that when we observe a supernova, we have a viewing angle. There is a line of sight, and we are not always observing the supernova edge on or the explosion as it comes to us. Sometimes the supernova is inclined, and we observe different inclinations of the event. And this can affect, this has been seen in models by Hoflich that are presented in the work of Davis et al. 2021, that for the same event, if you would consider different viewing angles, you could reproduce the shape of the light curve, but with different peak magnitudes. So could this be a mechanism to explain luminous events instead of CSM or weird things going on? It's just how we are observing it. We have also to consider that there are events that have shown different bumps throughout. Here you can see in the work by Brennan et al. 2022 that you can see bumps, different bumps throughout the evolution of the light curve of the supernova. And they explain this not only by different viewing angles, but the different distribution of CSM. So here is a combination between how I'm seeing it and what was the shape of the circumstellar material around the progenitor star. And so if you had a disk, for example, then you can explain these weird bumps that we see. And this to me is the key. So all the models that I have presented so far are all in one dimension. They are hydrodynamical models, but are all considered one dimension of evolution of the ejecta. If we go to 3 dimensions, we could see here, I present a plot from the work by Van Baal et al. 2023. We can see that the shape of the interior of the progenitor of the explosion that is happening has all these blobs. That is not an homogeneous sphere. So maybe it's a combination of not only viewing angle, but the viewing angle that coincides with the blobs of the asphericities of the ejecta that is happening.
But this is single star, this is not binary.
This is single star, yes.
Okay.
So what happens if to this 3D model I add binarity? What happens if I add CSM? So these are questions. I have no answers. Now, to add more questions is, okay, we have these models, we have the data, we will have so much more data when LSST is working, and this will happen at some point next year. So what I did, again, this is working in preparation. What I did was try to overimpose the footprint of CTF and LSST for the super-luminous supernova event. And already I see that if we consider the limits, or the quality limits of the observation, we have so few events that overlap. Why it is important that overlap? Because if we have two surveys observing the same event, then we will have a high cadence in the light curve, we will have a high cadence in the data that we get, and then we will have a good description. But if it's only one survey, then we will have large gaps. So we need to fix the problem of cadence of observations. This is work ongoing, so there are some surveys that are being planned to happen in the south. One that I'm part of is LS4, and we are very excited about it because we think we could fill in the gaps in the LSST data. Why is it important? You could say, okay, but if you see the actual light curves here in light red circles, there is the CTF observed data, and at the start is the simulated LSST data for the same event. And so here you can say, okay, but here LSST doesn't have such a high cadence, but it still recovers the shape of the light curve and recovers the color. So here you have different bands. And in this case, again, well, we can have cases like this where the full peak of the light curve, which is one of the most telling parts of the light curve, is completely missed by LSST. You can have cases in where you have no information whatsoever about the color. You think, oh, okay, early on, the evolution is like this, so we assume this color. And in this case, the behavior we can already see is different. And we have cases where, okay, I see the rise, I see the peak, I see the decline. This is the shape. Well, but because there was not enough cadence, we missed a very important second peak that, again, as we said before, could be telling us about the line of sight on which we are observing the supernova, or could be telling us something about the asphericities in the explosion. And with this, so many questions that I don't have answer for, I will conclude saying this. Since LSST was announced, there has been many efforts in trying to make the most out of the observational data that we have. On the side, theoreticians have done all their efforts to make ever more complete models. And they have gone to 3 dimensions, and they have added many explosion mechanisms. However, there seems to be a lack of synergy, and this is the fault of no one, just there's a complete difference in the paradigm of studying the data we have. We have to consider in only a couple of years, we went from having tens of supernovae to having thousands, and now we will have millions of supernovae. So we have to get ready, be prepared, make more efforts to see how are we going to deal with all this data. And again, in my opinion, the most important at this point is to know very well what are the most common type of supernova. And this, for me, of course, I would say if my work is important, and this is kind of, but I'm a bit biased. So studying samples could tell you, okay, these are the weirdos. These are maybe the ones that we don't understand, and maybe are the ones that will tell us a bit more about what we need to learn. And yeah, so this is it, and I accept all the questions.
Thank you very much. So I think we have plenty of time for questions if someone wants to ask something.
Maybe I went too fast, I'm sorry.
No, no worries, it's perfect.
I have a really naive, basic one. So at the beginning you said that, oh, we'd like to be able to classify certain events with less data.
Yes.
Right? And my question is, if you do that, isn't then the classification necessarily less reliable? Or I guess the question is, I suppose it is less reliable. How much less reliable will the classification be?
Well,
in that specific case?
Yes, so there are many works nowadays working all with simulations for LSST observations, and they find that they can recover the classification up to 80%. And when you are dealing with millions of events, this 80% is kind of enough. We will still miss many interesting targets, but maybe not so much because of a failed classification, but because LSST will go so deep that we will not have capabilities of following up the most distant events. So we will mostly be following up closer events anyway. And the classification now, so LSST, when it releases an alert, it gives the information not only about the magnitude that they observed, but also about the region where the supernova was found. And many times you can see the galaxy there, the hot galaxy, and there are also correlations between the hot galaxy and the characteristics of the supernova.
Do you know about I don't know if it has come to a conclusion, what is the LSST cadence?
Yes, it's supposedly now, but this is changing all the time and will probably change 10 times again before they start, but it will be twice per band per night. No, twice per band per 3 nights. So it will have the same band twice, and then gap of 3 nights, then the same band twice.
That's the normal, the white field.
But again, this will change, and I think this is the case. But maybe I'm something else. Yeah. But yeah, then there will be the deep drilling field.
Yes.
This will be a much higher cadence, but also much smaller area of sky. So the very good cadence will be just for very few events. But yeah, mainly you will have something like this when you have like two points and then a big gap and then 1 or 2 points. And because it's per band, the same band will have larger gaps.
So,
yes.
so it's either with the ZPF, you want to have the same observations at the same night, or you better fill the intervals?
Yeah, better fill the intervals. But the problem with CTF and LSST is that one is in the south and the other is in the north. So
but you covered the information.
Yes, there is an overlap. Yes. Yeah, but the idea is to fill in the gaps.
And what do you think? So you have a lot of models that are hydrodynamic observations that take a long time, and especially if you want to do 3D. So if you want to, like, you're discovering millions of supernovae, what do you think would be the best approach to try to fit these things? Or
This is the question for the theoreticians. Like, what do we need to make these models for these so many events? I don't know. Maybe the computational capabilities are still not there, but we also thought that the capabilities to store data were not there for LSST, and somehow they saved them. But we saved, we managed. Let's see.
I have like two. The first one is supercellular. I forgot what CSM stood for.
Yes, I'm sorry, circumstellar material.
Which I just forgot.
No.
The second one is just in principle, like you were talking about all these different ways of like considering the how the system is set up, like in the sky, and that
Yes.
can explain the different parts of the signals. But in the end, like, does that not like fit any possible shape? Almost, or
If we don't have any asperity, if things are
Right.
aspherical, asperity, sorry, if things are aspherical, then yeah, it could be, but we don't know because we have no overlap between so many models. And the efforts are there. It's just a matter of maybe having better synergies or waiting, which is sad.
But in that case, like if it's a single star without a disk, what is causing the asphericity? Like is it rotating or you haven't?
Well, many
Any
things that are not
functions?
considered nowadays in models is that you have different metallicities. Usually the models consider solar metallicity. There are some variations, but this is usually binary system models are rare. So you're also considered. So these are things that could cause asphericity. So difference in metallicities could have an impact because of the mixing that's happening in the hydrodynamics of the star. You could also have rotation. We are not considering rotation in the star. Yeah, and basically we don't know like what is the mechanism of the explosion. Only the core collapse is not enough for the ejecta to trespass the star, let's say. We need a shock revival, and in these cases, people are claiming that you have neutrinos, for example. But we don't know if this is the case. Asphericity in the explosion could help explain this better if you had, for example, jets. But the idea of jets is very controversial.
In which way?
We don't know what is forming the jets. Where are they coming? Right. Okay. If you have time, I have a bonus track if you're interested.
We do have time.
So I show everything about type 2s, but sample size of light curves are also very interesting for type 1s. And in particular for type 1As, that are the ones that people use for cosmology. And in this case, I study a large sample of type 1As in the I band. Already in the work by Colatelli et al. In 2010, if you take a hard look at the early portion of the I band light curves of type 1A, you can see a type of shoulder or kink at the early times. This is always overlooked, and it is considered to be an effect of cadence of the observation. So we studied the sample, and we find with derivatives, considering the second derivative, trying to study the changing curvature of the light curve, we find that most of the normal standardizable supernova 1A on the sample that we studied have this feature. And we also find that if we consider only those events that have the strongest feature, this kind of shoulder kink, if we only consider those that have the stronger feature, and we compute the Hubble residuals, which is the difference in the different modulus calculated from the supernova and the one calculated from the models of cosmology, we find that if we only consider these events, we reduce the Hubble residuals. And reducing the Hubble residuals is like the goal of cosmology. So this could be potentially very interesting. So yay for sample studies of light curves.
Sorry, so you think that just having the sampling of the Stockholm supernova light curve is correct? You might reduce the Hubble residual?
Yes, not in this case it's even easier than the infrared because it's just I band, so it's just in the so it's the redder part of the optical band, so it's easier to observe that.
Yeah.
Yes.
You say the one that I have less Hubble residual than the one with the kink.
Yes, the stronger one. So this is also a bit controversial though, because there are some works saying it's not accurate.
What do you mean is not true? If you can find a subgroup that has these properties, and you can just by using just them can lower the Hubble residual, it's good.
Yes, well,
No matter how they happen, it's super.
yes, but there are challenges towards the method of using the derivative. So there is a work. This is just me rambling, so stop me if you.
No,
There is a work that does the same study and say that we are relying too much on the Gaussian process because we are taking the derivatives of the Gaussian process interpolation. So they present, so this is the work by Stevens and Lee in 2022. They present their interpolations and their measurements of these parameters obtained through the derivatives, and they find that if they use different interpolations, the parameters only coincide half of the time, which would mean that there is a randomness to detecting or not detecting the feature.
I guess you need higher cadence.
However, no, my opinion is that maybe we shouldn't leave everything to the machines. So this is a bit controversial. I'm just presenting an idea. Because we have so many data, usually we tend to say, okay, we feed this we take the statistics, we have the result. Of course, we cannot look one by one to million of events, but maybe we can look one by one to tens to say, okay, what's going on? And since I had tens, not even hundreds, I did look one by one, and I did correlate the derivative parameter obtained from the first derivative, which gives you an idea of the slope of the light curve. And I compare with just the normal slope estimation, which is a difference in magnitude. And I find a strong correlation between this. So
Sorry. The slope, when? Because the slope changes in the light curve, so where is the slope?
yes, but we are interested in the slope of the light curve after the peak. So in this case, it's the slope of the declination.
So like the delta and also?
Yes, but just but this is just with the derivatives. And in this case, the slope I computed was the decaying slope for type 2s. And in this case, I do it delta m 1430 instead of between maximum and 50 days from maximum, between 30 and 40 days from maximum. And I found the correlation with the parameter obtained from the derivative.
Is the second, okay, is the second slope?
Yes, so in this case, it would be, if we consider here, it would be this slope, but in this case, I'm considering type 2s. So it would be this slope here, between 30 and 40 days. This since maximum, so it would be this slope here. Which to me, what I'm trying to argue with this is that the study of derivative is robust rather than random. But I think, and I encourage more studies on this, because it's easier to interpolate and derive and obtain parameters than to try to figure everything just from the observe photometric points value.
But then the question is how you interpolate.
Yes, and this is the problem. And this is the problem for the observational report. Yes. What do we use for interpolation? As I said, my presentation is all about questions, not much so much about answers. But I think the questions are interesting, the driving side.
Are there any more questions? Talking about questions.
So if you imagine that 1 year from now, you have bunch of supernova.
Yes.
What's your first search?
My first search.
Then the 10 that are moving.
So I think the biggest discovery would be a pair instability supernova. So this is the one thing that has not been really pinpointed right now. We have candidates, but we don't have striking evidence that we are seeing this. And we know what are the ingredients for pair instability supernovae. We know it has to have a long rise. We know they will be super-luminous, but we don't know much more. So ideally, if we find early on a thing that is taking really long to rise, we will shoot all of our telescopes to it and observe it very intensely and try to figure out if it's really a pair instability supernova. Not only because these events have not been pinpointed yet, but because it could revolutionize the study of stellar evolution, because as I said, pair instability supernova are believed to arise for more primordial stars that we haven't detected. So we could say, okay, we haven't detected a type 3 star, but we have seen the explosion of it.
We could even have one more question if someone wants. Well, if not, let's thank Priscila again.
If you enjoyed the video, like and subscribe.